Hello everyone, it's a pleasure meeting you all again in mathematics class. Today's topic of discussion is in random processes, a special topic called the Markov chain, and this Markov chain has already been explained to you in my earlier videos. You can go through them and it's well explained and problems have been dealt in Markov chains. And in this class, I'm going to discuss, I'm going to make a discussion on classification of states in Markov chain. That is, in a Markov chain, you'll have the states. Now we are going to classify the states according to its properties. For which, let me take an example. Let us consider this transition probability matrix. And if this is translated into a diagrammatical representation as the one I have drawn here, as per this transition probability matrix, we find that there is a communication between 1 and 2. And in turn, there is a communication between 2 and 1. And normally understand that if there be a communication between 1 and 2, there need not be 2 to 1 can be there. It is not necessary. Here in this case 1 to 2 is there, and all these are 1 to 2 happens with a probability 0.6 and 2 to 1 happens with a different probability 0.5, and there is a loop. You can find the loops at 1 and 2. That means probability of going from 1 to 1 and 2 to 2 are there. Likewise, you find that 3, 4, 5 are the states, and as per the transition probability matrix, the transitions are drawn. And you find that 3 is able to communicate with 4, 4 is able to communicate with 5. 5 may not be able to directly communicate with 3, but it goes from 5 to 4 and 4 to 3. And you see that they are reachable. 2 is reachable from 1 and 1 is reachable from 2. So we say that in a Markov chain, state I is reachable from J means there must be a path between J and I. And understand that one need not be reachable from 2. That is, the reverse need not happen. If it is given, it is given. Otherwise, it need not also happen. Okay. Here in this particular case, you see that 3 to 4 is there and 4 to 3 is possible. And 4 to 5 is there, 5 to 4 is there. Transition is there. But 5 to 3 is not there. But 5 to 4, 4 to 3, it can happen. And therefore, here you see that these two sets, class, we will call them as closed class. These closed classes, they are closed because there is no communication between this set and this set. And we define here a set of states, yes, in a Markov chain is closed set. These are all closed sets. If no state outside of S is reachable from any state in S. So you see that these two are closed sets and it cannot be reached from any other state. Therefore, these two sets are closed sets. But this is a Markov chain as per this transition probability matrix. Okay. Now, so here we learn what is called reachable, what is called a closed set, what is called a communication. Two states are said to communicate if there be a path. A path is nothing but a line, that is a line drawn from one state to another state that there is they communicate. So then, let me take one more example here. So this is the example that I am going to deal with. Before that, I require certain terms, certain terminologies. The terminologies of absorbing state. Absorbing state means once after transitions, if it reaches a particular node which is an absorbing state, then it gets absorbed, that it never goes for other further transitions. That is the meaning of that, for which I will give an example. See, here you see that this particular example that I have taken here, I will call it as 1. This example 1 is nothing but, this is an example of a gambler's ruin. That is a very famous problem in which a person gambles. A person gambles and he gambles with 2 rupees in his hand. And if he wins in a particular game, he gets 1 rupee. And if he loses 1 rupee. And he plays in such a way that, with the condition that, if he loses all his 2 rupees, he has to quit the game. And if he is able to get 4 rupees more, for 2 rupees more, that is, he has got 2 rupees, and if he is able to win 2 rupees, then he has to quit the game. In the sense that, if he has got 2 rupees, if he gets 4 rupees, then he has to quit the game. So, at 0 and 4, at 0, he cannot further play, because he gets absorbed in 0 in the sense that he has no money and he cannot further play. And if he gets 4 rupees, as per the problem, he has earned enough that he will stop playing, and therefore 4 becomes an absorbing state. In the sense that further play is not carried out. Okay? Now, so you see that I have drawn the probability density, that is the Markov chain I have here drawn here, a diagrammatical representation of that gambler's dream. Here 2 rupees he has got, 2 to 1 if he loses, and 1 to 0 if he loses the second rupee also. 2 to 3 if he wins 1 rupee, that is, he has got 3 rupees here, and if he wins more 1 rupee and he comes to 4, that he stops. You can see that these nodes, you can find that the probability of self-loop is 4 to 4 is 1, here 4 to 4 is 1, and 0 to 0 is 1, in the sense that it will be in itself, it cannot go out, it is being absorbed, it cannot go further. So you see that absorbing states are the states where the probability of the self-loop is 1. Probability is 1 to come from, to reach itself, and it cannot further step out. So these are called absorbing states. So when, here also I will make here you can find that this 2, if you take that node, that is state 2. State 2 to 1 is possible. State 2 to 1 is possible. That means he loses 1 rupee. If he comes to 1 rupee and if he wins, then he can go back to 2. He can go back to 2. But if he loses, he will come to 0. So 2 to 1 is possible. 1 to 0 is possible. But further playing is not possible. That means this 2 to 0 is, there can be a transition from 2 to 1, 1 to 0 is possible, but 0 to 2 is not possible. Therefore, we say that 2 is a transition state. The same holds good for 3. 3 to 2 is possible, 2 to 1 is possible, 1 to 0 is possible, but 0 to further is not possible. 3 to 4 is possible, because 3 to 4 he goes, but from 4 he cannot come back to 3, and therefore these 1, 2, 3 are called the transition states. Transition states are the states from where you can go to other states, but there is no return back path is available. There is no return back path is available. Therefore, these 1, 2, 3 are called the transition states. If they are not transition states, we call them as recurrent states. What are recurrent states? See, I have given here. If the probability, that is, let us suppose that here I have given the example of the recurrent state. Here 1, 2, 3 are the states, and I have given the probability of transitions from 1 to 2, 2 to 3, and 3 to 1. Even the loops are given here. That is, the transition from the state to itself are also given here. Now you see that here 1 to 2 is possible, 2 to 3 is possible, 3 to 1 is also possible. That means every state is reachable from every other state. What is that? Every state is reachable from every other state, and therefore it is a recurrent. The states are recurrent. And one more point I want to drive at here is that since every state is reachable from every other state, the states or the Markov chain itself is an irreducible one. So we call a Markov chain irreducible if every state in it is reachable from every other state. Can you understand? So here we see that this is an irreducible Markov chain, and here the states are recurrent. The states are recurrent, And recurrent in the sense that is you start from state I, go to other states, and you can come back to this thing. Definite that you can come back. The probability of coming back to itself is 1, which is being very clearly defined here. Fi of 1. That is, you start from I and come back to I after n steps. Fin means you start from I, come back to I, the same state after n steps, which is equal to probability of xn is equal to I, starting from x0 is equal to I, coming to at the nth step, xn is equal to I. In between, you visit the transitions are taking place in other states. The transitions are taking place in other states, but the final, if you come to the nth step, will be again the state I. If this happens with the probability, this is nothing but a probability, conditional probability. So if the conditional probability happens to be 1, then the state I is said to be recurrent. If it is not, if it is less than 1, it is said to be a transition state. Okay. So this is about what is called a recurrent state and transition state. I'll give you one more example in this. I want to talk about what is called the length. What is the length of the shortest path? Yes, here you can see that I have taken an example. 1, 2, 3 are the states of a chain, and 1 to 2 there is a path, and 2 to 1 is there is a path. 2 to 1 is a path. Now the length of the path here is 2. The length of the path here is 2. I have named it as k is equal to 2. The length of the path from 1 to 2 is 1 to 1. 1 to 2, 2 to 1. Therefore, k is equal to 2. That is, it is the length of the path. And understand that the condition, I will impose a condition that k is greater than. This is a very, very important condition for defining a certain term. I will tell you what that term is. So, I have given an example of a path which is of length 2 here. So 1 to 2, 2 to 1 is the shortest path and it is of length 2. And 1 to but you go for calculating the length of other all possible paths. In this particular case, it is 1 to 2, 2 to 3, 3 to 2, 2 to 1. See, 1 to 2, 2 to 3, 3 to 2, 1, 1, 2, 3. Length of the path is 4. And if this path 4, length of the path 4 can be expressed as 2 into k. In this particular case, k is equal to 2. So 2 into 2 is equal to 4. So you see that here you are able to express the length of other paths as the multiple times of the shortest path, the length of the path. That is namely 2. When this is provided, this k is greater than 1. That means you cannot take the loop, you cannot take, because when you put a loop, k length becomes 1. That the condition is k must be greater than 1. It can be 2, 3 like that. But if you go for finding out the lengths of other all possible paths, then all such paths must be multiple times of the shortest length. If that be so, then we say that the state has got the period k. It is periodic. We call this what? A periodic. So here this 1 is periodic with a period 2 and 3 is also periodic with period 2. So this we call it as. So here it is the shortest length, k is equal to 2. K is the shortest. K means the shortest length of the path. And if you find any other path coming, that means path means start from I, come back to I and calculate the length of the paths. And if the length of the path is multiple times of the shortest length of the path, then we say that the particular k is called the periodicity, or the state has a periodic with a period 2. And if it is not periodic, we call it as aperiodic. Example I give you. Here you go to the fourth example. 1 to 2, 2 to 3, 3 to 1 is that. Now what is the shortest length? 1 to 2, 2 to 3, you find that k is equal to 2 because the path is 1 to 2, 2 to 1, the length of the path k is equal to 2. Now you start calculating the lengths of all other possible other paths. I have taken the easiest, but this is enough because you can extend to any Markov chain problems. So you see that 1 to 2, 2 to 3, 3 to 1. That means 1 to 2 I have written here. 1 to 2, 2 to 3, 3 to 1. But what is the length of the path? It is 3. But this 3 cannot be multiplied, cannot be expressed as the multiples of k, which is equal to 2. And therefore 1, 2 are not periodic. We call them as aperiodic. And 3, of course, it is aperiodic. So this is an example. This is what we understand by periodic and aperiodic. Okay. Now I will come to the next one. I will explain that. See, what I have given an example. I have taken an example here. This is a transition probability matrix, and the Markov chain diagrammatic representation of it is given here. You will find that here 1 to 2, 2 to 1 is possible. 1 to 2, 2 to 3, 1 to here you have got here 2 to 1, see 1 to 2, 1 to 3, see 1 to 3, 3 to 2, 2 to 1 is possible. 2 to 1 and 1 to 3, 3 to 2 is possible. Then from 3 to 2, 2 to 1, 1 to 3. That means every state is reachable from every other state. Here in this particular case, every state is reachable from every other state, and therefore the Markov chain is irreducible. This Markov chain is irreducible because every state is reachable from every other state. And if you get a loop, try to understand that if there be a loop, then you will find that it will be aperiodic. The nodes, the states will be aperiodic. You will find that in this particular example, the Markov chain, the states are aperiodic. And that every state is recurrent in the sense that you start from 1, you can come back to 1. You start from 3, you can come back to 3. You start from 2, you can come back to 3. That means all the 3 states are recurring. So what are the three things that we have got in this? One is it is the states are irreducible. Number 2, the states are aperiodic, and that the states are recurrent. When these 3 properties or conditions are satisfied for Markov chain, we call the Markov chain as ergodic. See, this is ergodic for the simple reason that here they communicate with each other, they are irreducible, and they are recurrent, and they are aperiodic. The states are aperiodic. Therefore, this is called ergodic. Can you understand? Okay. Now, let us come to this. So, this is ergo. Now, I am taking one more example here. Consider this Markov chain here. The transition probability matrix is given here, and this is the diagrammatical representation of it is given here. As I explained to you in the first example, these two are closed sets. These two are closed class, and there is no communication between these two. And that here the initial probability is given to be pi is 1 by 5, 1 by 5, 1 by 5. There is equal probability for 1 to go for 1, 2, 3 equal probabilities are given here. We are asked to answer certain questions as if any stationary distribution, then n is equal to pi. We have to say whether it is stationary, that is whether steady state stationary exists. You find that, see, we will ask, I will try to answer certain questions here. See, we say that, when we say that, and try to understand that we can talk about the steady state probability or steady state distribution, one stationary distribution, only when the system is ergodic, only when the Markov chain is ergodic. Ergodic in the sense, it must be the states are recurring, the periodic, and that every state is reachable from every other state. That is irreducible. If that is so, then we say that particular Markov chain has got a stationary distribution, or that steady state probability exists. Now let us come to this. Here you see that this, say state 2 and 4 they communicate, whereas 1, 3, 5 communicate, whereas there is no communication. That means what? They are reducible. They are not irreducible. They are reducible. Try to understand that reducible means if there be a probability, we can always make them irreducible. You can always make them irreducible if we can just give a probability of 2 to 1 or 4 to 1, make some changes so that it becomes irreducible. But if there be no communication or reachable from one state to another, even for one, then we say that it is reducible. Here in this particular case, these two are closed sets, there is no communication, and therefore the Markov chain as such is reducible. So once it becomes irreducible, you see that it cannot become ergodic. So once it does not become ergodic means naturally the steady state probability does not exist at all. There is no steady state probability. That is, the stationary distribution is not. So this is all about. So I have given 2 examples and I have taught you the meaning of this. We shall see more problems in the coming days on Markov chain and other problems. Thank you.